Okay, we can look. I'll look there for the. Okay. Okay. Sorry? Just? Okay. So good morning, everybody. It's my great pleasure to be here, invited as a moderator with Vladimir for this morning session, first session of today. And first of all, let me thank the organizer, the staff, the technicians, and all of you for being here. I think this day will be even more exciting because we are willing to talk about AI and AI in a wider perspective we're used to, in the sense that we'll try to move from research into operation, but having a wide angle perspective, including also possible implication on data policies and risks that come together with AI. So I strongly encourage you to participate in a question time to provide your feelings, your impression on the presentation that will be presented today. So the aim, the rationale of the session is to bring together scientists and experts to present us the latest development in the AI world, the challenges related to the data management and how to cope physical modeling and artificial intelligence to perform to the best into existing operating meteorological and hydrological systems. In the first part, we'll have the great opportunity to hear from scientists from ECMWF with a keynote talking about the latest development at ECMWF on earth science. And after the presentation, we'll have an introduction of the panelists for the discussion and briefly introduce them, and then moving to sort of debate, so discussion on different points that I already introduced. After that, we'll have a question time open to all of you, also to the online participants. And okay, now we can start with the keynote that will give you the possibility to setting the stage of the transition from research to operations in weather and climate prediction. I have the pleasure to introduce Peter Dueben, should be online. Peter,
yes,
are you
I'm here? Hello. Hi there.
Hi, Peter. Nice to see you. And Peter is the head of the Earth System Modeling section at the European Center for Medium Range Weather Forecast, ECMWF. ECMWF, of course, is the world's leading global weather forecasting center, famous for the IFS, the Integrated Forecasting System. Peter is also honorary professor at the University of Cologne. In the past, at ECMWF, he was the AI and machine learning coordinator in the time where ECMWF was starting pushing all the energies in this new world. I remember very well the commitment of Peter in this activity, and at the same time he was University Research Fellow of the Royal Society, performing research in use of machine learning, high performance computing, and reduced numerical precision in weather climate simulation. Currently, Peter is the coordinator of weather generator. I'm sure that will present us briefly also this very interesting project under our Horizon Europe project. The aim is to build a machine learning foundation model for weather and climate application, and it has been also the coordinator of Malmstrom Euro HPC joint undertaking project. The presentation of today by Peter will focus on ECMWF latest AI forecasting system, AIFS, to advancing numerical weather prediction from research to operation. And then, Peter, is up to you. You have 25 minutes, including question time.
Thanks a lot. Thanks for inviting me, and sorry that I can't be there in person this week. It was too difficult to travel. But I'll hope you will still enjoy the presentation remotely. I'm going to talk about what we do with machine learning at ECMWF right now. And I mean, just in general, you know the drill. We do weather forecasts, so we have data simulation at the beginning, and then we kind of generate initial conditions. Then we have the model, and then we have the products and the predictions going out. And with machine learning, I mean, you're also all aware how these kind of the big global models are in principle working. So they take data from reanalysis data, reanalysis like ERA5, for example, that's also produced at the European Center. Then you have like a time series of a couple of decades, and you just learn the update like from one stage to the next. And by doing this, you basically learn how to kind of make a prediction once you have initial conditions. So the machine learning models are still based a lot on kind of the analysis products of the physical model. I will also talk briefly about approaches where you can also do data simulation with machine learning. But in general, I think what we have operational right now is really taking the analysis and then basically doing predictions. And we have both a product that is AIFS single, which is a deterministic forecast, and also the ensemble forecast. And it's no surprise to you, this development is not really very old, right? We basically pushed these two operational products now online this year, and we kind of started with the whole process in 2023. So it's kind of really the timescales are just absolutely amazing in comparison to normal timescales in our domain. Just a couple of words how the models are working. So AIFS single, that's a deterministic one. The basic idea is that you kind of take different time slices as inputs. You basically have global fields, and you can take them as inputs, 6 hours apart, 2 of them. And then we have a step that we call the encoder. So the grids of the model is basically kind of transferred into an icosahedral grid that is then used by the machine learning model. This step is very easy to do because we have so-called graph neural networks, which means that we can basically digest whatever grid you want to give it. We can basically build a graph that is kind of making this mapping, and how this mapping is done exactly is kind of learned in the process. Then we have what we call a processor. That's the step where you actually do the time stepping. If you want, you kind of really kind of progress the model further. And there it's important how kind of connect the different dots on the sphere. And then there's an encoder step where you kind of then basically go back to the original grid, and you have the output, and this output is then 6 hours ahead of it. So you basically have a prediction of 6 hours, and then you can iterate the process, and you can make longer predictions. And it turns out that these models are competitive. You all know this from GraphCast and ForecastNet and so on. But obviously also for AIFS, we are competitive. And I just brought you one result, which is the tropical cyclone tracks, where you see that the error in red here for the machine learning models is lower than the error for the kind of original physical space model, the IFS. So great success here in the sense we have a very good model. You also want to kind of get the ensemble right. So you also we're talking about medium range, so you definitely want an ensemble. Again, how do you build this with machine learning? It turns out that there are actually good methods to do this, and there are kind of mostly 2 different methods. One of them is a so-called diffusion method. The idea here is that you start from noise, and then you kind of build up structures. You learn how to build structures from noise, and by doing this, you can kind of basically generate small-scale features in a coarser picture. for example, but you can also then generate variability in an ensemble using the same method. That's, for example, used by Google in GenCast. In our case, we're doing it differently. We actually kind of base our ensemble on what we call a score-based method. And the idea here is that you basically, you start from an ensemble, you start from initial conditions, you run kind of, you produce different ensemble members if you want, and then you actually kind of make a loss function in the machine learning model that is kind of taking care of the ensemble characteristics. So you literally put in the ensemble loss function into the training procedure. This has the advantage that you can basically train the ensemble natively, the disadvantage that you to some extent have to run a couple of ensemble members in parallel to actually be able to evaluate the CIPS loss. Long story short, we get very good results again with our ensemble model in comparison. So again, I brought you one example, T850 hectopascal with the IFS in blue and the AIFS in red, and you see that the AIFS is clearly outperforming the IFS in terms of ensemble scores. There has been a lot of skepticism about those models in principle, right? I mean, when Google produced the first GraphCast result, everyone was basically saying like, yes, you may have a model that is score-based and kind of basically producing nice results for scores, but you won't necessarily have a model that is good in producing extreme events and be physical, basically. And I think that's a little bit unfair in a way that these models are actually more physical than you may think. So they actually produce physical kind of consistent states that are not really kind of totally different from a physical model in principle. And they are also performing fairly well for extreme events, kind of much more so than you would maybe expect just by the pure setup in principle. And I just brought you one example. This is the storm Boris over Central Europe, and you basically see the observations on the left with a lot of precipitation happening over 72 hours. And then there's some noise in the background. And then you have the IFS system in the middle, and you see the forecast was kind of fairly good in the way that the precipitation is roughly where it's supposed to be. And then you have the AIFS forecast on the right. And you see the AIFS is clearly less detailed, which just comes from the fact that AIFS is running at 25 kilometers, IFS is running on 9 kilometers. But the forecast itself was actually pretty good, also in terms of that it's get the extreme values right in a way. And also in a sense that the signal was kind of fairly consistent over the forecast lead times. So we actually see this quite often that AIFS is performing well also for extreme events. And it kind of, maybe we don't need to be so skeptical as many are in a sense that the models wouldn't be able to do that. Just one slide. So far, basically, a model like AIFS is still using the analysis from the physical model and also the reanalysis for training. But there also is an approach we call AI-DOP at ECMWF, where we basically do the whole training procedures from observations to observations. So that would basically just get rid of the entire process of a physical model itself, because you never use it in the chain. You just have observations coming into a machine learning model and observations going out as predictions. And this is kind of quite a step and quite a bold step in principle, because normally the background in data simulation, for example, is helping you a lot getting the state right, yeah. But actually the results so far look good in a way that you can actually get like good predictions. Here are two examples for severity predictions and on the left and targets on the right. And you see basically how the model is doing well in terms of the representation, and also like to do some forecast at least a couple of days, we also already get good results. So I think at this stage, no one can tell you whether this is going to be beating the physical modeling at some point, but it's definitely something very interesting that should be watched in the next 1 or 2 years. This is just one mentioning. I think machine learning gives a huge amount of possibilities as well for collaborations. And I think this is really kind of, it has been great to see how also like the meteorological community was kind of helping themselves in a kind of community effort. And I think the best example for this is kind of the Anemoy library, which is kind of developed between the member states of ECMWF and ECMWF. It's an open source library. And this is really showing that if you have kind of like a task to do, like doing weather forecasts with graph neural networks, for example, nowadays is actually very good to kind of really pull resources together and kind of develop the libraries in a way that people can use them for different applications. And this has been very successful in a way that many of the Met services are now considering going live with models with machine learning based on the library. And we also have recently kind of received an award from EMS showing that this is kind of really something that has impact in the scene. Okay, another avenue now. So far, AIFS was mostly focusing on the atmosphere. Yeah, right. You basically build an atmosphere model that can be used for predictions, but there's no limit in principle to other components. So there's also an approach that is really driven by destination Earth, where we kind of now also extend the pure atmosphere component of AIFS, if you want, by a lot of other components, like one for land, ocean, sea ice, waves, and hydrology. And then basically, eventually, you can also kind of drag the impact sector into the mix with their own machine learning models once you have this kind of Earth system model character. So I think that's really one of the leading problems or the really leading challenges for us now to kind of make models that go beyond AIFS in a sense that they actually represent the full Earth system. And that's something that is kind of progressing well at the time. So just I can't really go into the details of all the results, but just to give you a couple of snapshots. So on top left, you have basically wave fields that we get if we kind of couple wave dynamics into AIFS based on these destination Earth models. And you see that basically the waves are represented well. That wasn't too surprising to me in a sense that I expected the model to do well for the waves in principle. What was surprising to me was actually that these waves are really also physical waves in the sense that they're not just a diagnostic of the wind forcing producing waves, but actually you can really see the waves propagating through the whole Pacific, for example. And so it's quite physical as well. Then we obviously look more into hydrology and water. So we have precipitation fields now, and we're looking also into river runoff, and I'm going to present 2 slides on this in the next slides. Then we also look into the ocean. So this is sea surface temperature. We also have a 3-dimensional ocean model that we're developing. And there are interesting questions how to couple this back into like an atmospheric model. Do you have an isolated ocean model that you then couple to the atmosphere, or do you kind of put the whole things together and train them at the same time? Very interesting stuff. And then we also have sea ice that you can also kind of now be basically, well, represent in the machine learning model as well. So a lot is happening in this Earth system complexity part. Just one thing to go a little bit deeper, even though I'm not the specialist here, so I hope you don't have too detailed questions. But since this kind of meeting is also about like floodings and hydrology, I thought it was good to give this example. Which is also part of Destination Earth. They basically look also into like a machine learned flooding model. And what's going to happen here is you basically take your dynamic forcings, for example, from the reanalysis data and the weather forecasts. You also have time and periodic inputs, and then you have static catchment information. And then you basically train machine learning models to kind of make predictions for the forecast into the future. And what they use is so-called LSTMs, which is basically a regression method. So a repeating method. So you basically kind of keep the history in the machine learning model and progress it forward, and then you can predict the discharge. And they get good results in a sense that they are now competitive with the model with kind of tools like the one from Google that was made quite a splash when it was published in Nature last year. So in general, I think we're seeing good results. I think the problem here really is what's the quality of the data? Like what do you have as information in the data? Because you need that to really make good predictions. And for specific different rivers, you have different kind of amounts of data available. Okay, that was basically kind of talking a lot about the pure machine learning model, but obviously you still have the physical model, and there are different ways of how to combine the physical model and the machine learning model. And it has been very interesting to see a method that is called nudging now. And this is kind of a fairly simple method in principle that was first explored by the Canadian Met Service, and they showed basically it's working very well. And the idea here is that you take your IFS, your physical model, and you nudge it towards the AIFS, which is the machine learned model. And what you get in the end is basically, and you do this at very, very coarse resolution, T21, like literally thousands of kilometers resolution. And by doing this, you basically recover a lot of the benefits of the large-scale scores that we get from AIFS, but you also keep the small-scale features of the IFS. And this means that often you kind of basically get something like the best of both worlds. So this is, for example, this is an example. I'm sorry that I think the figure quality is not very, very well, but what you see is basically you have the mean position error for tropical cyclones on the left and the maximal wind speed on the right. And for the position error, AIFS is in green is producing the smallest error, whereas IFS in blue has a larger error. And the hybrid model is somewhere in between. So it basically gets the positioning of the tropical cyclones right in a way, following AIFS. But on the other hand, if you talk about the wind speed, the physical model is actually much better than the machine learning model. And here again, the hybrid model is actually kind of following the physical model because it has a small scale details. So to some extent, nudging can give you the best of both worlds. There are a lot of ifs and a lot of things to consider. For example, if the AIFS would increase resolution, maybe you would get the best of both worlds anyway, and you would maybe not need nudging. But just to give you an example, I think this is also something to be watched because there's going to be a lot of development there. I think it was already mentioned, weather generator. It's just like a bit of the question, what is coming next? And one potential thing that kind of may change what we do with machine learning in weather and climate is to go towards those so-called foundation models. It's a buzzword, it's totally overloaded. But what we mean by foundation model is basically a big model that is taking a lot of different data sets as input. This can be reanalysis data, it can be simulation data, it can be observations. You basically bring to the problem whatever you have as data sets. And then you have a very large machine learning model in principle. And then this will be able to give you very different output sets as well. So you build a more generic tool than just a tool that can do a specific task and a tool that can basically serve a lot of different applications. And the hope or the ambition of the project that we have here, it just started in February, so we're still at the early stage. But the hope is, and eventually you should be able to kind of bring whatever input you have for the problem. You should get whatever output you want. And you should be able to do that on a global scale or local scale at resolution levels of like 100 meters locally or 100 kilometers globally. Whatever you have, you can basically use. And this is based on a so-called self-supervised training approach. So the idea here is that you basically just fill in gaps. And by doing that, you make it easier to train from large data sets. And then we should also go to very large model sizes, much more than we have today, basically. And the hope is that then you would basically build a very generic tool. So you would have the weather generator as a very large latent space representation in machine learning. And if you have satellite observations and your output is reanalysis data, you do data simulation. If you have IFS initial conditions and you kind of look into the future, you have a forecast model, and so on and so forth. So the idea is really that you should be able to basically use that tool in a lot of different contexts. And in the project, we're doing this with 22 applications. So we're exploring the space kind of across a wider range of applications. And it's all very ambitious. In the end, to be honest, we don't know yet how successful this is going to be, right? This is a research project, and to some extent, it could be that a task-specific model will always beat such a generic model in the end. But it could also be the other way around, and there's only one way to find out. And weather generator is our best bet there, I guess. Just to say, we already have produced first results, but I'm not going to go into detail. It's also an open source tool, so everyone can join and help us with this if you want to. You are very welcome to. It's basically everything is kind of developed in the open space, and we would be very happy to engage with you. Challenges for R2O, just to mention, there are challenges, obviously, now with machine learning coming to an institute like ECMWF. I mean, the first challenge is kind of quite simple. If you have two systems, you have two systems to take care of. So you basically double the amount of systems you need to think about and keep in mind. So that's kind of stretching your resources already. And you also have more products. And that's kind of like in itself a problem. On the other hand, obviously, there's a benefit from the products. Another thing is, so AIFS also needs to work well with the initial conditions of the physical IFS model right now. And this is normally happening quite naturally. And you kind of basically, you train on ERA5 and then you kind of retrain on the latest analysis and you get a model that is working well with the initial conditions. But when you upgrade the physical model, this also brings problems for the machine learning models then. So what's actually going to happen is often, or at least in this current cycle, we really saw that the physical model upgrade would change how AIFS is running from analysis products. So we basically need to now also make sure that AIFS is retrained whenever we upgrade the physical model. if you do hybrid IFS, AIFS, and I'm not saying we're definitely going to do this, but if you would consider things like nudging for operations as well, you come with a whole sorts of different set of problems. So you would need to run AIFS first, and then IFS would use this data in operations, and so on and so forth. So you have a lot of kind of internal links between the different products, and again, it makes your life more complicated. And obviously, AIFS is not yet of the same complexity level. So we only have 6 hours time steps. We don't have all the fields that the users need. So again, we have kind of, it's not doing the whole job yet, basically. I'm very confident that we will get there, but at the moment it's still a little bit like you still need the 2 systems in parallel, and you still need to kind of, well, there's a lot of information from the physical model that is not yet available from the machine learning model. On the other hand, machine learning is giving you a great opportunity as well, because you can run these models on a single GPU, which means you don't need your whole supercomputer thing. You basically can do this on a single GPU somewhere. And there's what we call also a model-in-the-box approach, which is also supported by Destination Earth, where you can really just run your model somewhere as kind of an entity. And that's something totally new, right? I mean, IFS wasn't portable to any other machine before Destination Earth for a very long time. And now you have suddenly a tool that you can move around. And then you can also think about producing the data where it's needed rather than kind of moving all the data around. So it's much easier to actually use these models externally as well. So there's also a lot of opportunity here. Okay, just in general, I think we're kind of changing a little bit the concept of Earth system modeling right now with machine learning. So far the concept was always that we basically we design the best possible model configuration for weather and climate models, in particular also for weather, and we then use it for daily predictions. But now we're kind of getting to a different realm where we basically we use the model and the observations and to produce data sets. And those data sets are then used to kind of produce machine learning models. And the machine learning models are then used to basically, well, do whatever the user wants to do with them. And this is true for the past, present, and future. And it's kind of something that, again, brings a lot of opportunities, but it also brings challenges. And just to mention one of them, it will be extremely easy to generate very nice looking flow features, for example, for whatever weather you want to look into with a machine learning model by a single PhD student somewhere with a GPU. But it will be very difficult to verify what the model can actually do because it has learned it from the data. And that's not so problematic for weather, but it's clearly very problematic for climate. So I think one of the biggest challenges that we will also have in kind of R2O processes, in particular for the longer lead times and eventually also climate simulations, is that we will get a lot of information, we will get a lot of results, we will produce very beautiful pictures, but we will not really be able to often tell when we are not right. So when the model will generate something that is kind of, it hasn't really learned. I'm not going to dwell on this too much, but it's something to be kept in mind. And I think the important part here really is that you need to challenge whatever you see in that space, right? We always need to kind of really make sure that we challenge the developers as well to show that what the model, to show that what they show the model is supposed to be doing, that it's actually kind of also learnable from the data. That's kind of all I had to say, and I think I'm within the 25 minutes. Just one outline. I think R2O wouldn't stop necessarily just in the model development. I think R2O is also where machine learning will also kind of have a very strong impact in the future is also in how we use the forecasts. And this is just like a bit of an outline. In the past, we basically were listening to BBC Radio 30 years ago to get the weather forecast. Now we have internet browsers and mobile apps and so on, and the next generation would probably kind of just somehow get information from TikTok or other tools that I don't even know anymore. So there's definitely a change of how we digest information in principle. And with machine learning, you can think big as well. I mean, you can think about a way where people would just kind of make a picture of whatever view they have from the living room, and then they can scroll through the picture and see how the weather would be changing, for example, in interesting apps, right? So you can also kind of combine visualization much better with information that you generate. And I think that's something we should look into. The same for climate. I mean, just think about not just getting error data from in a grip format from a web portal, but actually kind of be able to scroll through whatever you have in the neighborhood in terms of videos or pictures, and just look how the weather has changed over the last 40 years, and then also look into the future how, for example, extreme events could look like. And then if you combine that with LLMs, you can open a new space basically. Then gaming, I'm not going into detail, but you can also think about how to really have realistic weather in gaming scenarios with virtual reality. And also for planning, I think how you use weather forecasts, I think there will be a lot of change in the future because people will basically just say like, okay, next weekend I don't have anything to do. What can I do? Where's the weather nice? Should I go climbing or should I go to the sea? And that's all I had to say. Thanks a lot for your attention.
Thank you very much, Peter. Very impressive presentation, and you set the stage for the discussion of this session. I don't know if are there any questions from the audience or online. Very briefly, because we will have a dedicated question time after. If I may, I just read one in the chat from Ricardo. Is the weather generator model completely data-driven? For example, generative or autoregressive transformer?
Yes. So basically, we will get a lot of different data sets in, and there's no physical structure or equation in there, basically. So it's transformer based, and the answer is yes. Yeah.
Okay, very good. Any question from the audience? Quick question. I don't see any. So now we can move. Peter, I'd like to have you in our discussion. So stay online and feel free to intervene during the discussion. In the meantime, I would like to introduce you our panelists. There are a couple of them are here in person. The other two are online. Firstly, I would like to introduce you Dr. Stefan Dietrich. Stefan is a Senior Scientific Officer and Deputy Director of the International Center for Water Resources and Global Change, which is a UNESCO center hosted by Germany Federal Institute of Hydrology. He coordinates international water data activities and advocates for global freshwater in situ observation network. Stefan is currently the Director of the Executive Secretary of the German National Committee for the Water Programs of UNESCO and WMO. I'd like to emphasize that Stefan in WMO is the co-chair of the task team for global hydrological data centers, a member of the task team Earth Hydronet and advisory group for hydrology of WMO Infrastructure Commission, INFCOM. Thank you, Stefan, for being here. And the next here with us is Viju John from EUMETSAT, who is the science team leader in the climate group of EUMETSAT, with more than 30 years of experience working with satellite data and creating climate data records from measurements from space. In the past, he worked at the Met Office Satellite Center, then coming to EUMETSAT in 2013 to work on creating fundamental climate data records of infrared and microwave sounders and imagers to create so-called essential climate variables. These data records are essential to monitor climate change related to water and energy cycles. Online, we have the pleasure to introduce you Dr. Bertrand. Yes, Bertrand Lesseau, who is the, sorry, just to find him, my papers. Bertrand is the policy officer for the, Bertrand, are you here?
Yes, good morning, everyone.
Okay, Bertrand Lesseau is the policy officer for the green transition, Destination Earth and AI application in the DG Connect at the European Commission. Its main interest is tackling practical problems that arise in Earth observation and Earth science to bring solution to current environment and society challenges. It is an impressive background and curriculum in Earth observation, working in many centers of excellence and institutions, just to name European Space Agency in Italy, and he also co-organized many workshops and events in machine learning for Earth observation, and also set the ones that, for example, ECMWF hosted recently on machine learning for Earth system observation and prediction, and the weather forecast competition at NEUR IPS and humanitarian assistance and disaster response workshop. So welcome Bertrand. And finally, last panelist is Simon McClellan from UK Met Office, and is also here as a WMO officer, because Simon has over 30 years of experience in various roles at the Met Office in UK, mostly on management and governance of environmental data. So is also was a key player with Schubarel, WMO, playing a leading role in the development of the WMO unified policy that is essential in the discussion today. This is aiming to the international exchange of Earth system data, and now it leads the implementation of this policy as a member of the INFCOM of WMO. So you can have an idea that the panelists can help us to enlarge our point of view, our horizon to have a different perspective on AI. So we can have here ECMWF and EUMETSAT as world leading centers to exploit the potential of AI. At the same time, we have the hydrology world with Stefan to give us the opportunity to enlarge the domain to the hydrology and possibly to the other domains that are interconnected as a unique Earth system that we are considering in science. At the same time, there are implications related to the data policy, so data exchange, data infrastructure, and Simon will be really beneficial to address these points. And last not least, the importance of having a European Commission here to move from research as a bridge towards operation and to serve the community with new tools and boosted by AI, enabled by AI. So the discussion will be very interesting from different perspective. I strongly recommend you to give your point of view on this perspective. Very briefly, I will let you to introduce yourself with possible hints for the discussion. So we'll start with you, Stefan. So you should have a few slides to accompany your speech. I recommend to stay to 3-4 minutes maximum.
I think that is possible. Yeah, first to all the organizers, thank you for the invitation here. Yeah, as said, I work for at the BFG, the German Hydrological Service, but here we are connected, or we are hosting our International Center for Water Resource and Global Change here, and that is a UNESCO center, and maybe something for you who are interested also in this transition from research into operations, also UNESCO is active, of course, in doing hydrological research, and we have this nice publication published last year of applications of AI for water management. And I also have a poster outside where we can discuss a little bit what we have done. So sorry, that's for German, but we had a couple of weeks ago only a German organized workshop from the German Water Science Alliances and the BFG, where we also looked into AI and machine learning into also ready for operations. So next slide, please. But I will talk a little bit about data scarcity, let's say my own field. Thank you. What you see on the right-hand side, that's a figure from my colleague Simon Michel. He's also here, is heading the Global Runoff Data Center. And what you see, the brown spots, what you see here, that are data deliveries globally exchanged older than the 1990s. So more than 30-year-old data. The green one are more the newish ones, but I mean that is a global picture which we do observe with all the global data centers. Might it water quality, might it soil moisture, might it groundwater, and in similar aspects. However, there is also related to AI a big chance, no? Because first we can match, and that is, I think, what Peter Dueben also mentioned. We can match now a little bit with other data like satellite Earth observations. We can use the models to fill data gaps, and we'll show some examples. Next slide, please. That is also done by GRDC with colleagues from the University of Stuttgart. What you see here, now it changed. Okay. What you see here, in principle, is a similar map as in before. The black dots are the active stations, so the greenish ones in the slide before. The grayish ones are the outdated stations, and the bluish, that is our extended stations by Earth observations. So now we can come up with, let's say, a better infill data. We work on that also for the different parameters, so soil moisture and water quality as well. Next slide, please. And that is another example to infill from the colleagues from ECWRGC. They used generated in 2024 global hydrological reanalysis. I mean, that is now bringing all that fields together. So next slide, please. Here's a study now that's not really now a little bit into the ocean, but I think that is also the aim, what we can see on the horizon, also to do that on the continents. On the land, it's of course a little bit more difficult than in the oceans because more difficult structures in terms of topography and so on. But what has been done, you see here is Argo data, so observations into the oceans, and they compared the pre-Argo time, so in the 1960s, and the Argo time a little bit later, and they infused all the different methods what they have. No? And what we see here, maybe on the lower pattern, you can then resample some of the geophysical features. No? And that was not be possible in before, but I think with a combination that is key. And now I come to my last slide, and to do that in hydrology in particular, this slide is next slide, please. Thank you. So in do that, we have to improve the data exchange. And what we really lack in hydrology, what we really do lack is that we do not have a common data exchange format, that we do not have a common and operational setups of metadata descriptions. I mean, nationally, they are really diverse. We know that from the work also of the data center, so really you have to work with everything. But I mean, that is really the big thing which we do have on the one hand side, and we have to work on that. And if you have also colleague here, or yesterday colleagues from the EU, and if you are here in Region 6 together, I think we, for hydrology and for the hydrological departments and authorities, we really need this umbrella, I would say, come from WMO together with the EU and work on that improvement of data exchange. What we have in the meanwhile in the WMO is a WHOS, WMO Hydrological Observing System, which is a broker system because we don't have the gold standard, we don't have this metadata. And that is an interim solution, I would say. We're looking also for with 2.0, but that is where we work on. And the second point is we have also to analyze the influence on AI on the observation architecture. So I think here's also big potential because we see a decline of observations globally, and I think we can do that better if we integrate all, but that's also a matter of research. Thank you.
Thank you, Stefan. Now up to you, Viju, to set the stage from EUMETSAT perspective.
Thank you. Thanks to the organizers for inviting EUMETSAT into this forum. And I'm also very happy to represent EUMETSAT here and engage with you all. I will just give you a few glimpses of what we do in terms of providing the best possible satellite data for monitoring weather and climate. That's our mandate. So I thanks for all contributions from my many colleagues at EUMETSAT. Next slide, please. Yeah, here I just want to show a major activity we do on providing input data for reanalysis. Peter has mentioned that the reanalysis is the key for many of the AI research and development that is going on here. Google, Microsoft, ECMWF, everyone is using ERA5 for the training. And the good quality of reanalysis data is pivotal for the good results coming out of the AI, research and development. So we have a direct agreement with the Copernicus Climate Change Service, or ECMWF, to provide a lot of input satellite data to go into the next reanalysis, that is ERA6. I cannot go into the details of all the data we give, but here what I want to show is this is a particular instrument that was flying on US Defense Meteorological Satellite Program, DMSP. It's a microwave temperature sounder instrument, and that was measuring from 1991 to 2005. And these data were never used for data assimilation or any other weather forecasting applications. So what we did is we rescued this data from US archives. We quality control, recalibrated, and created a fundamental climate data record and gave to ECMWF for testing to assimilate in ERA6. And this is what you see as results. You see in the upper plots the lots of blue. That means there's a significant reduction in forecast error, especially in the southern hemisphere and also in the stratosphere, where the other observations are not very dense. And in the lower panel, you see the better fit to radio zone measurements, for example. That is also showing the improvement of the analysis fields in the reanalysis. This is just a test results, but we hope that this is going to improve the temperature representation at ERA6 much better than ERA5. Next slide, please. Yeah, this is another major activity we do. So here on the middle, you see a quilt made out of all the geostationary satellite data measuring from the mid-70s to until recent. So all the different colors represent one satellite, one geostationary satellite each, operated by EUMETSAT, the Japan Meteorological Agency, and NOAA. And there are like 50 plus different instruments there, and they all come in different formats, different quality, and different calibration standards, and so on. So what we do is we consistently quality control, consistently calibrate, and produce a consistently mapped data so the user doesn't need to worry about from which satellite the data is coming from, what's the quality, and so on. So you will get global fields of this data starting in the late mid-70s or late 70s. And you also see that there are some gaps in the middle of that quilt in the early years. And so that is before we moved our Meteosat satellite over the Indian Ocean. But now we are working also with the Indian Meteorological Department. They have the data from the INSAT, that's Indian satellite data, to fill that gap. So there's a lot of data rescue activities also going on to achieve these kinds of projects. Next slide, please. And this is another example. We create a feature database. So features includes a tropical cyclone, extratropical cyclone, atmospheric rivers, contrails, and so on and so forth. So what we do is we create a label database of all these kinds of features, and this work is done on the European Weather Cloud, and this will be a very good training database for the users. Next one, please. And this is an example showing, the deep convective system database. This we have done with the researchers in France, Lagos. It's a research institute there. So here what we did is we provided 40 plus years of data record from Meteosat data on the European Weather Cloud. And they came up with their software to the European Weather Cloud, and they produced this the deep convective system there, database there, and this is now available through EUMETSAT for anyone to use it. I think that's it for me to just to show.
Thank you very much, Viju. And now, Bertrand, can you briefly give us your perspective? Have you few slides on your Bertrand?
Sure. Yeah,
okay.
Sure.
Up to you.
Okay. Do you see my slide correctly? Yes.
Yes.
Seems so. Okay. So, good morning, everyone. Happy to be here, and thanks, Antonio, for the introduction before. So, just briefly, I wanted to introduce Destination Earth, which is the project of building a digital replica of our planet by 2030, which is funded by the European Commission. So digital twins means maybe a bit more than the weather models than we have seen before, as so clearly explained by Peter. By a digital twin, what we want to do is not only being able to monitor, not only being able to predict, but also being able to play what-if scenario, to really have an interactive tool to be able to understand the phenomena, but also to ground decision-making in this understanding of the Earth system on the Earth system phenomena. So this is a novel information system that is funded by DJ Connect at the Commission, DJ Connect being the DG responsible for the development of the technological infrastructures, the digital infrastructure, including AI, including also HPCs and many other infrastructures in Europe. Funded by the commissions, but implemented by three trusted entities that are actually quite usual suspects. I am very pleased to see two representatives of these entities also in this panel. ECMWF first, because they are developing the core digital twins. I will go back to that after, on the digital twin engine. EUMETSAT, and as Viju has just presented, EUMETSAT is responsible for data and responsible within Destiny for the data lake. And then the European Space Agency, ESA, for the platform of Destination Earth. So this is a synoptic view. Let's delve a bit in the details. First, building a digital twin of climate with a very high resolution, 5 kilometers. And of course, being able also to go from this high resolution climate projection up to 2050 to the impact sectors, and being able, for instance, to serve energy, agriculture, disaster response, and all of this. The other digital twins, core digital twin, is the Extreme Weather DT, Extremes DT for short, which is actually running daily and producing 4 days ahead projection forecast at 4.4 kilometers. This is run by CMWF on their contractors. And when there is the risk of an extreme weather event, being able to trigger a regional, very high resolution model, again, to be able to respond to that. And this is a slide that Peter already presented. There are commodities, but of course, the ambition is much larger than that, going to model the Earth system, likely thanks to AI and even frontier AI models, and to be able to go from the commodities to the various components of the Earth system, and then to the impact sectors. Now, the Destiny has been, the first prototype has been released last year and open to the public in 2024. We done the basis of users on the open access policy in last July. And your single entry point, and this will be my last word, is the Destiny service platform. This is where you can onboard Destiny and use it. And this is my main message today. Please try Destiny. Please use Destiny, because there is already excellent data models and infrastructures and possibilities for you, but more will come in the next years.
Thank you, Bertrand. And now, Simon, up to you.
Thank you. Do you have my slides?
Thanks.
Hello. Perfect. Thank you. Yes. Good morning, everybody. Dobre rano to all of those people there in person. Unfortunately, I couldn't make it to the beautiful city of Prague this time. As you heard earlier, I work at the Met Office in the UK, but I'm presenting today as a member of the Infrastructure Commission, and particularly the coordinator for the implementation of the WMO Unified Data Policy. Next slide, please. So the Unified Data Policy, more formally known as the WMO Unified Policy for the International Exchange of Earth System Data, is something that was developed during lockdown. We developed, drafted, and got it approved at Extraordinary Congress 4 years ago, all remote and online, working very closely with Dr. Sue Barrell, who brought us all together to deliver this fantastic policy. And my challenge now, stepping into those shoes, is to coordinate the implementation of that across the WMO members, across the various standing committees of INFCOM, but also looking at CERCOM and the research board as well. I think that this document was written very much in line with the Earth systems approach that others have mentioned and across the WMO, but also looking to sort of increase focus on bringing all of the players to the table. So in the document, I carry a copy with me everywhere. In the document, there are annexes, particularly looking at engagement with public-private sector, but also engaging with the research communities and sort of guidance on how to collaborate across those Earth system domains at a national level, as well as at an international level. I think the policy continues the excellent work from previous data policies on weather, climate, and water, looking at that free and unrestricted exchange of data, and very much sort of highlighting the importance and the reciprocity of exchanging data, rather than just perhaps a one-way flow of data, but getting something back for the data that you contribute to the community. I think that's a particular challenge in some for weather, where weather does not know borders and boundaries, and that exchange of that flow of weather around the planet requires the flow of weather data around the planet, and perhaps sometimes that's more of a challenge in areas in water, perhaps, where there is a flow of water through various catchment areas and river basins and the like. And then the challenge there is looking at how we can share data at that local level, but understanding the needs of that globally, particularly as we start to look at the excellent presentations that have gone before, looking at how we can use local data to predict on a global scale. So it maintains a two-tier approach to core and recommended data, and they're described in general terms for each of those 7 Earth system domains. But the specific details of what data are considered to be core and what are considered to be recommended regularly updated, but held in the WMO's technical regulations, which means that we don't have to rewrite this policy every time there's a change to those things. Next slide, please. Just re-emphasizing that when we talk about core data, that's the data that shall be exchanged on a free and unrestricted basis. Ideally, there's a second tier of data, the recommended data, that we'd love to be exchanged on a free and unrestricted basis. And so rather than saying you shall do that, we say it should be exchanged in that way, but we recognize that there may be conditions that the data providers may need to place on the use of those recommended data. Attribution is always strongly encouraged in all cases, and we're looking at how licenses can provide a more formal expression of those conditions of use that may be applied. But we encourage everybody to advocate for that sort of exchange of data between the operational communities and the research communities. There's huge amounts of data that the research communities have that could potentially be really useful to the operational areas of WMO as well, and the global meteorological community. Next slide, please. So, summarizing, I think this may be my last slide. The role of this data policy is to ensure that the essential and equitable exchange of data by and amongst states. This will enable effective use of data in the development and delivery of products and services to all of those that need them, but only if the implementation of the policy is a priority for the various constituent bodies and members, which is why the policy that was written was designed and approved with implementation in mind, provides a framework for allocating those implementation tasks. And that's the approach that we're taking through WMO, looking at how we implement this data policy for the benefit of all. I think that's my last slide.
Thank you, Simon. And this completes the introduction for the discussion. Have you seen that the different perspectives have been well described and well presented here? So I would like to have your feedback on a set of guiding questions that we have prepared for you. Bearing in mind that you have a different role with different roles at different institutions, where maybe you can give us the state of art regarding the in particular regarding what just to echo what Peter said in his presentation, that the new approach to the new paradigm for the science using artificial intelligence is now to prepare datasets, to create datasets. Datasets are essential in the sense that, let me just move forward in the sense that the real power of AI, considering it is a strong AI, is also the possibility of discovery. So in the past, we were used to empirical, theoretical, computational science. Now with the artificial intelligence, we can have the possibility to discover new things, new phenomena. And that's the reason why it is really, really essential to have good data sets. So the real point here, and I would like to have your feedback on that, is the data sharing, the frameworks and the infrastructures, and possible also the implication regarding policy. How can data sharing frameworks and AI tools be better integrated into existing operational systems? So what's your feedback, your feeling on that, Stefan?
Yes, thank you. I mean, first, I will focus a little bit on climatology again, and I think I've put some already in my presentation. So the challenge is that we have still a fragmentation, and if I would like to focus also on Europe here, I mean, globally, if you see in the big data scarcity is particularly more in the global south, but if you focus here on regional assembly 6 and in Europe, I think there is a big potential. First, I think most of the member states in the EU have now really good data things, and the EU has really helped with Inspire thing and open data policy to advocate and also not only to advocate. That is also what we in WMO do. When we have issues, we advocate, but let's say the hydrological service are not listening to us. But to the EU, they listen. No? We have Inspire and the open data policies are implemented. However, it's still difficult to bring the data together. No? And that is the second point. I mean, of course, in WMO, we generate the guidelines. We have active task teams and expert teams and standing committees to do that. There's one which is called WIS for Hydrology. So here we develop actively how it could look like that we improve the data, this data exchange. However, we really need the help, and I see a big potential here if WMO and EU stronger collaborate here in Region 6 to bring that forward, because via EU we have the legal possibility to put it to the member states.
Thank you, Stefan. I'm pretty sure that we also think about the open data policy regarding the facilitation of this task, at least for Europe. Viju, what is the EUMETSAT? You presented us EUMETSAT strongly committed also through Destiny, but the European Weather Cloud was mentioned in your presentation. So the data infrastructure, there are examples of the users or services that are using the infrastructure you provided. Have you any sort of feedback in terms of usability of the platform in your institution?
Yeah. So European Weather Cloud is. Yeah, so the European Weather Cloud is a very good example of bringing the users of the data to the data than dealing with all the downloading and dealing with all the format issues and all those things. But what we have to make sure is we provide the best quality data on European Weather Cloud and the tools for dealing with all the different formats and also dealing with the quality of the data. I mean, many times users just use the data without looking into the quality and so on. So what we try to do at the moment, I mean, it's a lot of effort to get all our data on the European Weather Cloud, but we are slowly getting there. For example, I showed this example of the deep convective system development. So what we did is we provided all our Meteosat first generation and second generation data in a consistent format with the same quality and same calibration standards. So the researchers just had to apply their algorithm on that. But it's an iterative process. They always find problems, they feed back to us, and then we improve our data. So this is a co-creation. I mean, this is actually, I mean, it's getting a buzzword these days, but co-creation is really working with the data. I mean, working with the users. I think that is the main thing. So then you also learn a lot. Otherwise, you always think your data is the best. I mean, unless you get feedback from users. So this is the best approach. So we are getting there. Also, you may know that we have lots of satellite application facilities for various field like hydrology and climate monitoring and so on. They are all moving their data processing to European Weather Cloud. So we are also, I mean, we are providing the facility there, the data storage and also the computational facilities, and also we are learning a lot from them. What are the pitfalls in our data format and quality and so on, and we are regularly improving, I mean, our data quality and also data provision. So this is very important. Co-creation is very important. Work with the users, bring the users and learn from them and improve the services.
Thank you. Thank you, Viju, because the co-creation is really, really nice keyword to be kept as a take home message for today. And Bertrand, what is the Destiny perspective, also considering the approaching, the upcoming phase 3 of Destiny related to the possibility of implementing AI tools in these data infrastructures?
Okay, I'm sorry because I just had a network issue just during your question.
I asked you about the potential of Destiny, in particular for the upcoming phase 3 the program related to the AI tools. So they implemented the sort of empowering AI through AI the possibility within Destiny you presented, the digital twin.
Okay, thank you for that. So indeed, as I said in my earlier talk, now we have a Destiny that is open for use. We have a single working prototype. And now the idea is to move to operations ready by end of phase 3. We are currently in phase 2, which will end next year, and then 2 more years for phase 3. And of course, since the core is done, the idea is to move towards the impact sector to really provide applications which likely will be powered by AI, by frontier AI models. Because one thing that would be very important here is to be able to model the cascade effects going from weather or climate, but then, for instance, to hydrology, since we are in a session about water and hydrology. And of course, then it has an impact on society, on the communities which are along the rivers. And this is typically something where we need collaboration, because this is by essence cross-border. So yes, in terms of AI, I guess that this AI modeling all these connections between different sectors will be
also considering Bertrand, that the HPC infrastructure made available within Destiny is using the best HPC we have in Europe. So it's natively ready for AI. So it's really impressive.
Indeed, because it's a strange animal. I mean, the world we are in, because there are 3 legs. So there is AI, there are data, we discussed that, but indeed there are also the infrastructure, the computing infrastructure that you're running the model and processing the data on. And here we had already Euro HPC, and Destiny is making a lot of use of Euro HPC through our partners. But now there is also this Commission ambition to be ready for becoming the AI continent with the AI continent strategy, which means, and we already delivered the first AI factories. Now we have new calls for AI, for Giga AI factories, to be able to serve competitiveness on research on all the society developments related to AI within Europe. So indeed, this is a major strategic axis in the next years.
I fully agree, Bertrand. And now, Simon, you mentioned that, from one side, we have now a really good data policy framework provided by WMO, unified policy, but we have still the responsibility to implement it. So what, to your perspective, to your experience, also you came at office, the data sharing could be how could be better integrated into operational systems. So what are your warnings on that?
Well, thank you. It's really interesting to hear the comments from others, and I think you might have mentioned it yourself. Co-creation, collaboration, these are clearly things that we can't do as individual members, and that collaboration, particularly in Europe, is really important. Clearly, not all European Met services and European nations come under the sort of the EU, but it's very much a case of sort of need to collaborate on such things. We talked about Inspire, we talked about open data exchange. I think for me, in terms of the implementation of the policy, I think what some of the greatest strides are in the sort of the systems, the WMO systems, the WIS. I was delighted to see that WIS has been mentioned more than once. At the moment, I'm working with the ocean community and looking at how we can get ocean observations sort of better integrated, not just a case of looking at ocean communities data policy alongside the WMO data policy, but looking at their observation data systems to integrate those into WIS as well. So I think WIS serves as a potentially great backbone as we start to understand more across some of these other domains of the Earth system, what data sets we would consider to be core and recommended, and how we can use WIS to get those data more readily available, shared, exchanged with people across various communities that need them.
Thank you, Simon. And finally, let me ask Peter on the similar question. You presented ECMWF as the world leading in implementation of an operational AI system. That is really impressive. Also considering the time frame, in the sense that we met in Reading just a few years ago, preparing the project, and now it's in operation, so it's already available for our weather forecasters in our operational rooms. And that's really impressive. So a specific question to you, moving to this operational side. What's your feeling about the use, so the exploitation of the products made available by AI from a user perspective? Because you know, yes, our weather forecasters are used to consider weather maps as the product of a physical model, so they are used also to be a bit proactive, finding deficiencies, failures, misses, and so on. With AI, the risk could be, what's your opinion on that? The risk could be to have lack in this very important feedback from weather forecasters, because they don't know how the system is producing this output.
Yeah, I mean, fundamentally, it's similar in a way that the AIF is producing data and the user is going to take it, and the forecaster are looking at it, and I mean they're looking into the same fields to some extent and so on. I think it, however, you're absolutely right. I think this kind of chain from the model development to the forecasters, and in particular also the feedback from the forecasters to the model development, is getting more and more important, in a sense that we really need to, I mean, first of all, we need to make sure that people trust those models. If they don't trust them, they won't use it, and then it's for nothing, basically. So that's really important. And we also need to really understand where the deficiencies are and need to take them very serious, maybe even more so than for physical modeling, in a sense that we really need to understand, like, what are the deficiencies and sort them out. So I absolutely agree with you that the trust building is really the essential part, and the community is conservative to some extent, right? I mean, it will take a lot of time to actually kind of really build trust over time. And the feedback, therefore, is very important. And I think we do this. I mean, just to give you one example, I think the first thing that we've done with machine learning models was actually to kind of take existing models like GraphCast and run them internally and provide the results online for everyone to look into this. To kind of, I think that's really important, that people actually kind of get access to the data and get an understanding what the models can and can't do, and then also kind of feed that back into our model development. So building trust will absolutely be essential, in particular because these models are very good and they can be trusted. I honestly think so. I think we need to get the message across as well, and are very proactive there.
Thank you, Peter. And this is also an invitation to the audience here to look at the products and also possibly give feedback on the quality, on the possible improvements. Now, if I may, I would like to have the feedback from the audience, letting you to raise questions or to our panelists, also online. Maybe we have one. But before that, is anybody happy with asking question here? I can't see any. Have you the microphone? Is the Petra? So I don't see. Okay, Adina.
Thank you very much. Adina Croitoro, Working Group for Research, and also dealing with data exchange with the research sector in the research board. My question goes to all of the panelists, or who wants to respond. And as a non-technical person, basically I'm a climatologist, not an AI person. How important are the non-conventional data? So not data not collected by national hydromet services or any regulated organization, like citizen science data. And with this respect, how important is the data format for assimilation into AI models or applications? As usually, these non-conventional data, they come in different formats. Thank you very much.
Thank you, Adina. And now, rapidly, loop of answer.
Yes, thanks. I think thanks for the question. I think in particular for hydrology in global fields, as you've seen, we have this decade-long data scarcity in the global south. And there's a lot of going on in terms of citizen science and also, of course, research. It's a matter. Trust is always a matter, so we also try to make them to authoritative data, so that, let's say, a hydrological advisor or permanent representative gives okay, but that is quite often still difficult, even if long-term observation networks on the research sector have been implemented. So that is really a matter for advocating that. It's a good thing. And another aspect is, again, if you look in Germany, we have now a big consortium which is called the National Research Data Initiative. We have the SE section, Earth Systems, Science Informatics at the EGU level. And man-wise, I mean, if you look at the people who meet in Vienna each year to the EGU meeting in comparison to that hall here, that is incredible woman and manpower which we should use. So, and that is maybe also lessons learned. Of course, we have in hydrology in data exchange format, which is the XML format, so WaterML, WaterML2, but it's not used. No, and the thing is why it's not used, because we don't have open libraries, we don't have generic viewers. Let's say let's say another example is NetCDF, Climate Forecasting Convention, and all the tools which have been developed. Having an easy to use Windows tool to visualize something and things like that, that is really, really important, I would say.
I think that's a very good question. In my opinion, the quality of the data is very important for AI training and development. I don't know whether the quality of the citizen science data is good or bad, but it's very important that there's a mechanism to scrutinize the quality of that data before it goes into the training. I'll tell you one example. When AIFS is using the data, the ERA 5 data, the input data is heavily scrutinized and blocklisted and all those things before it goes into the assimilation. Because there's a big mechanism before the data assimilator. All the bad data are thrown out before it goes into the assimilation. And Peter mentioned about the direct observation prediction. So we are in direct dialogue with and a constant dialogue with the DOP development people. What they want is consistently reprocess quality control data for the direct observation training. They cannot just use all the data for training. So the quality is very important. There should be mechanisms to scrutinize the quality before it goes into AI training and prediction.
Thank you, Vijay. I think it's a sort of a paradox, because the data deluge now is also exposing us to the risk of so-called brain rot. So the artificial intelligence has too much to deal with, and so it is really, really challenging to find the signal inside the data, the latent signal.
At some point it will get so intelligent and deal with all these problems.
Yeah, that's an interesting point. Maybe we still need, Adina, we still need the human intelligence together with artificial intelligence. Absolutely. So, because if not, we are lost. And Bertrand, what's the answer to Adina in terms of destiny and EU perspective? We lost you. maybe. Oh, maybe. Okay. Okay, Bertrand, bye.
Yes. Maybe it will not be Destiny's perspective, but more generic, because saying that indeed there are, in my opinion, two issues with data here. The first, and it was mentioned previously by Peter, is about evaluation. It's also data quality, on how we can have, how we can assess, not data quality, the results of AI, the AI results, for instance, assess the quality of the AI results. And for this, we need, of course, data for evaluation. And since AI is able to produce results at unprecedented scales or at finer resolutions than ever, we need data that were not available before, just to understand if the results are trustable or not. And there is another issue, which is about training of the new AI model. So we have various levels on standardization. Before, the challenge was to collect data. Then it was to collect and to prepare analysis-ready data. And now it's to prepare AI-ready data. That is data that actually will be a bit agnostic of the expertise of the system, before it was a human, of the system that will analyze and process it. And this is quite a big challenge, because it means that you need to carefully go through all the process to prepare this AI-ready data in order to have something that is really interoperable, and that you can mix data coming from very different fields, from weather, from hydrology, but also all these kind of things at various scales and various resolution. And this is a big issue. This is an issue that, so I'm coming back to your question, we are addressing in Destiny through partner EUMETSAT and on ECMWF mostly, to produce this kind of AI-ready data and to be sure that we have interoperability with different sources of data. But this is a long way to go, I think.
Thank you. Thank you, Bertrand. Simon, what about the importance of having such non-conventional and also the interoperable data formats and of course, implementing data policy? You mentioned the recommended data that should be shared, but are not mandatory. So the role of Met services in particular.
Yeah, no, it's a really good question, Adina, and I think some really interesting thoughts from the panel. Taking it a slightly different way, I think there's always within WMO the understanding of the services to the user communities. That rolling review of requirements. What data do we need? And perhaps those data aren't necessarily needed as inputs into the AI model. Maybe those non-traditional sources of data, those non-traditional data types, are more relevant for verification, developing trust in those models, but also starting to think about observations of impact. You know, that idea of what the weather will do, what's the impact of certain of those forecasts, and can we look to verify the impact as well as to verify the science of improving the accuracy of the weather forecast. So I think there's really interesting debate there to be had on what would impact data be capable of offering in terms of verifying not just the accuracy of the forecast, but also the turning that into a service with impact. Briefly, though, on the ever-increasing volumes of data, the ever-increasing accuracy, I do feel for the weather forecasters, you know, those operational meteorologists who are then trying to create that service. I think there's work to do, perhaps, where AI can help them understand, from AI is creating yet more models for them to consider when they're putting that weather story together. What role can AI play in supporting them in distilling the relevant versions, the relevant nuggets of information in this sea of data generated from physical and AI models. So I think there's some really interesting research that can be done in those spaces as well.
Thank you, Simon. Finally, a million-dollar question to Peter, just echoing what Adina said about the importance of data, the observation, which are essential. Also, looking at the point in the chat regarding the benchmarking of the AI model, and then we have a final question, maybe the one here online. But before that, Peter, you mentioned that it is important to have an integrated approach. So looking at also the future, what's your vision regarding how far are we related to the full integrated Earth system AI modeling, and what are the real challenges, the barriers on that at the moment?
Yeah, I think we're actually fairly close in a way. I think Europe is actually in a very good position here. I mean, a lot of people are always saying Europe is behind and stuff like this, but actually in Earth system modeling, in the physical modeling, and also in the machine learning modeling, Europe is actually very well ahead, or at least on par with the developments there. So I think we are very close to get very interesting tools. I mean, tools like AIFS are already there. Tools like with Destination Earth, with the Earth system modeling, are going to be there very soon. Tools like Weather Generator is going to be available very soon, and I think it's going to open a new space that is going to be very, very flexible for machine learning applications. So I think we are close to kind of also being able to kind of as a not just have developments in some silos, but actually kind of as a community to really kind of make the next step. And I think the biggest problem to some extent is still machine learning is obviously a science that is kind of very straight in a way that you just go into one direction, everything is working, but it's a lot of trial and error. So I think we will, the challenge to some extent is to do a lot of trial and error testing with kind of very large tools and smaller tools and combine different observations to each other and stuff like this and see what's actually working well and what's not. So I think that's our task.
Thank you, Peter. Thank you all for the answer. Because the time is over, I think it's important just to have a final question, if any. We have one there. In the meantime, I would like, if I may, just to translate what Felipe asked online. It's fantastic. I really appreciate this question, Felipe, regarding the integration, the possibility of integrate risk or socio-economic data in the training of AI model. And that's really nice to improve impact-based forecasting. This is sort of a message also for you, for your institution to keep in mind, because I fully agree with this approach, because the potential of AI could be even more. Up to you.
Thank you for offering me the last question. Max Steinhausen from the Technical University in Braunschweig. I'm curious to hear from the panel what the efforts in the field are concerning the explainability of these AI models and the results that come out of these models, and how you communicate the uncertainties of these models, especially when it comes to extreme events. Thank you.
That's a really great question. Maybe this is really important to have a very quick answer, just a few words from all of you.
Maybe brief, because I will give that to the experts, but that is also a matter of the data quality in terms of the data which are coming as, let's say, the raw data into the AI models. And in hydrology, we are not set up in a global perspective to exchange uncertainty. So we are delivering mean levels. I mean, here starts a problem already, you know. So big point for us is also still training and capacity development, not only in the global south, but that is also starting in Europe, no? That we improve our data quality.
It's not really my turf, but for weather prediction forecasting, the explainability may not be that important, because you want to see, I mean, a good forecast. But when it comes to climate, you really want to understand the process. I mean, why something is happening. For example, yesterday we heard about EMOC, whether it's declining or collapsing and so on. AI may predict something, but there we really have to understand understand the uncertainty of AI predictions and so on when it comes there. Thank you.
Very quick from Bertrand.
Yes, can you repeat the
explainability? The explainability of the AI model is an important step forward to improve the usability also.
Sure. So indeed, on the thinking of Destiny, this is something that we try to support, especially. I'm not sure it's not bringing more uncertainty, but with chatbots, with agents, which are able to explain also and to give some insights and retrieve some climate or weather information relevant for the question of the users. So this is actually quite related to the capacity building that was mentioned before. But of course, there is maybe more that explaining the results. There is the issue of assessing the quality of the results, the uncertainty of what is produced. On this, on of course, of the predictions, especially in terms of climate. On this, actually, is one of our ongoing efforts. We have recently established a new group of the Strategic Advisory Board of Destinationers, which gathers lots of scientists and experts from meteorology, but also from the impact sectors. And hopefully, with this group, we are also able to drive the strategic directions for the future and for having more user adoption.
Thank you. Very quickly, Simon.
I'm absolutely not the expert in this field. I think I bow to the expertise for the others on the panel.
Okay, thank you, Simon. Peter, up to you with final words.
Yes, thank you. A very, very important question. And there's a lot of research, really interesting research going on in explainability of machine learning tools. I mean, to be honest, it's difficult, right? I mean, if you have a tool like AIFS with 200 million degrees of freedoms to actually make an explainability study and really understand the nitty-gritty details is probably going to be impossible to some extent. So we have to probably admit that often we have a black box there. I think Viju made a very good comment. I think for weather, that's not so bad, to be honest, because we can test what the model is doing for extreme events. We do this on a daily basis for years, and we haven't so far seen any problems. And I think it's kind of probably even more reassuring than just trying to explain the details there, basically. But for climate, it's going to be an issue. For climate, this really means you will have tools that will give you results that will be shiny and nice, but you don't really know exactly whether this is provided for the right reasons. So I think this will keep us very busy there.
Thank you very much, Peter. We are just missing a final question from Utah here. Just to read it, the importance of the possibility to use AI to influence data collection, so sort of an adapted approach to assess the ground truth. That's really nice question, real nice also way forward to consider AI power also in terms of setting up the new data gathering for improving the systems. So let me just thank all of you for the participation, active participation, also online, and thank you all, and stay tuned with the forum. I'll leave the mic to the organizer to any logistics communication. If not, we can enjoy the coffee break, coming back at 11 if I may suggest to stay on time. Thank you.